this one. Yeah. Straight. Thank you. Okay. Okay, so let's start the final one. So yesterday, okay, we computed the partition function using a localization technique and find the dq, d eta, d eta bar, df non-zero equal なんだ違うこれじゃないあれこっちかequal to あれどれだこれかマイナス 4 pi squared over 1 so there is a cancellation between the fermion and boson and there is no dependence over n or something like that. Actually, because of the pairing, this one factor cancelled. Okay, and okay, then index equal 2 pi. Okay, sorry. And here we use dq, d eta, d eta bar df is defined by this dq 0, so dq 0, d eta 0, d 0, and df 0, and non-zero mode. Non-zero mode is measure is defined by here, yeah, with coefficient is 1. Here, yeah, we just add this one. Because of there is ambiguity of the path integral measure, and it should be determined by compared with operator formalism case. For example, in this case, using harmonic oscillator, it's a free field in a corresponding path integral theory. We can compute it directly, and then we can determine this one, like a Feynman Heaps textbook. So this is a measure. Then this one becomes 2 pi, 1 over 2 pi minus 1. And remaining things, this is a localized things. Path is like this one, times exponential minus beta alpha f0 squared plus minus w prime q0 f0 minus q0 eta bar 0 eta 0. Okay, these terms are coming from the tree-level action at the localized things, I mean zero mode. Okay, this comes from the isotherm delta I, from delta I or delta V. Okay, and this thing is remaining because F0 is not a classical, I mean saddle point solution. Okay, and then this can be computed. First of all, we integrated this one. This just gives this one. So this becomes dq0 minus infinity w2 prime q0. This is a factor of this one. Okay, and df0, this is an auxiliary field anyway, exponential minus alpha beta f0 plus 2 alpha beta over I times w prime q0 plus, sorry, minus alpha beta or w2 prime q0. Okay, this is sorry, squared. We rewrite this one like f0 plus something squared or something. It's a use. Sorry, this is a squared. So this last one is of course squared. Okay. This is trivial calculation, and then integrating out this f0 gives some Gaussian integration by shifting this one to f0 and this one. Here we shift the path of the f0 by this I factor here, but actually there is some, yeah, we think f0 as some holomorphic variable, so we can take any path in a complex plane, not on a real, just a real, but real plus some shift in imaginary direction. Anyway, so then this gives 1/2 pi times pi over alpha beta from this Gaussian integration times this one. No. Okay. Q0 exponential alpha beta over squared, sorry. Squared. Okay? This is trivial, just a Gaussian integration. Then we can equal dw prime. Okay, and okay, here we x, then this is dx. Okay, then this integral becomes, if there is some possibility, if q0 is infinity, then w prime infinity, and if it's minus infinity, then this case, sorry, minus infinity. This case, this integral is just use integration of minus infinity to plus infinity. Okay, then this is just a Gaussian integration for this dx. That gives 1/2 pi I times pi over root alpha beta times this factor. That is pi times alpha for alpha beta. And this is 1. And 2, if w prime is minus infinity and w prime is plus infinity, if q0 is this case. Okay, this case, this integration is plus infinity to minus infinity. Okay, it's reversed. So this gives minus 1, like here, but it's reversed. The sign is changed, minus 1. And 3, w prime is plus infinity, and w prime is infinity, or w prime minus infinity case. This case, the integration is infinity to infinity or minus infinity to minus infinity. Of course, it's 0. So this is 0. Okay, so this is a result for computing the index using a localization like a technique. Okay. Okay. And okay, and we can see this result is same as previous computation using operator formalism, because this means potential is like w prime. So this is like this one. Yes, so this is w prime is infinity, so it's increasing. Here it's decreasing. This case it's like this, and this case this like this same or inverse. Okay, so this is same as computation of the index. Okay, so then we can, this is related to the Nicolai mapping, but anyway, we can compute the index. It's like that. Okay. So okay. So in using a very completely different method and a completely different way, we can reproduce this result. And indeed, this doesn't depend on alpha, beta form of the superpotential because of this asymptotic behavior only contributes. So this is a properties of index. Okay. Okay. So this is a typical computation in a localization. Expanding around the zero mode and compute the free theory. It's called one loop determinant, and then integrating out these variable or just a formula. Okay. Okay. Then we will go to the n equal to Suzy QCD, a supersymmetric quantum field theory, general quantum field theory on S3. We can apply localization technique to this theory, but actually we need many preparation. First of all, we need to consider the theory on S3. Okay. So so this theory is a dimensional reaction of the 4D equal 1 if we compactify the S1. So the we can use almost the same notation as or same formula as the 4D equal 1. Okay, but for the n equal 1 case, on a Euclidean space, Lorentz groups or rotation groups is like SU2 times SU2. This is index alpha and this is alpha dot. At least, more precisely, it's SO1, 3, then alpha and alpha dot. But in a 3D case, Lorentz groups, rotation groups, is just SU2. So there is only alpha indices. And this SU2 is embedded in this SU2 cross SU2 as a diagonal. So diagonal means this alpha and alpha dot are the same. Okay. So we can, in a 3D, we do not distinguish alpha and alpha dot. Okay, only the one type of spinor, wire spinor. So there's no chirality in 3D. And gamma A, this is a Dirac matrix. And we take this as a Pauli matrix. Pauli matrix satisfies the Euclidean Dirac matrix relation. Okay, and you use this notation. Sorry, if psi equal alpha beta gamma e beta gamma psi gamma. Actually, sorry. For this types superconducting fields, localization Supercolumn theory and application of localization to such theory is this reviewed in the paper I introduced yesterday, Pestan et al.'s review. It's actually very huge, 1,700 pages or something. So this in the review there is some chapter on this one, and also this is notation of this one is almost same as so this is about this theory and related one, especially related to the AGT things, but here we just consider this one. Okay, so this is a notation. It's almost same. C is an unsymmetric tensor, and okay, like this one. This is only alpha indices. So psi bar and psi is the same representation of the Lorentz group. And here and gamma m equal gamma a okay, gamma a m. So this is a flat space notation, and we will move to the on S3. So this is a Vierbein. This is a Vierbein, okay? So it's of course in a flat space Vierbein is trivial. So gamma m and gamma a is same, but I will use this notation because for its same notation can be applied for this S3. Okay, so this gamma a is a gamma matrix on a flat space, and this is a gamma matrix in a curved space. And then the chiral multiplet, like for the n equal 1. Okay, it's a dimensional reaction of the chiral multiplet in 3D. So this includes phi bar, psi bar, f bar, and so this is a Suji transformation scalar. This is for the my okay. F equal okay. So this is a Suji transformation for this 3D n equal 2 case. So actually this is almost same as n equal 1. We can find this one from by the dimensional reaction of the previous Suji transformation. But of course we need to big rotate the one direction, time direction. Anyway, and here we wrote down this without chiral multiplet, but we will see, including chiral multiplet, there is we need the other term, and plus I epsilon phi bar sigma, and here minus I epsilon bar sigma psi plus lambda bar phi minus I epsilon psi bar sigma minus phi bar lambda. Okay. And here we introduce, lambda is a vector fermion in a chiral multiplet, but sigma appears here first. And actually, sorry. Okay. Vector multiplet is maybe I vector multiplet. Okay, is in a 4D. It's a lambda alpha alpha dot and d. Here mu is 1 to 4 in 4D. In 3D, this becomes AM, m equal 1 to 3, and A4. We will call sigma. And lambda alpha, there's no dot in 3D, and then d in 3D. So this here, this A4 is scalar. So vector multiplet in n equal to 3D case have a gauge field plus one auxiliary field plus two wire fermion plus one scalar. So this is a physical one, not auxiliary. Okay. Okay. So this is like so if this scalar have a VB, it's like n equal to in 4D. This is because adjoint field. Okay. So it's the theory becomes a Coulomb branch. So n equal to theory has a Coulomb branch giving VB to this y. And this sigma. So the sigma and lambda appeared here in a Suji transformation. Okay. So maybe you ask why these terms appear, because this can be seen from the superfield or something. But in the previous lectures, we fix a West-Minot gauge. Okay, and in a West-Minot gauge, if we there is some gauge fixing condition, and if we act a Suji transformation, then West-Minot gauge is violated. So then we rotate back by the gauge transformation to the West-Minot gauge, and this gives this one. Okay. So user. And here psi alpha, psi bar alpha can be considered as independent. Regard independent variables in okay. Psi and psi bar can be independent. As a midterm model case, there is no psi dagger or psi bar dagger here, so everything it's okay to think like that. And for the vector multiplet, transformation is So this is a Suji transformation. Okay, so this is a same, I mean, almost same as for the n equal 1 case. We have not written that explicitly, but this is okay. So this is a flat space case. So to apply the localization technique, it is convenient or more rigorous to compactify the manifold on a compact space. Typical one is S3. So we will consider next this theory on S3. So we need a supersymmetry or field theory on curved space. Okay, that subject is not so typical in a particle theory community, or at least for the student. But anyway. Okay, so S3 is defined by, as usual, this one, and L is radius of the S3, and we introduce to M. L equal 1 over 2M. M is then have a mass scale. Okay, so M is related to the curvature of S3. Okay, this is not flat space. There's a curvature. Okay, so this M is a curvature scale also. Then a way to construct Suji on curved manifold is one way is just expanding by this curvature. In this case, M. And adding terms order by order. Order by order means by expanding M, then first things is M equals 0, so R4, then this is okay, everything is okay. The next order M, there is something bad, so we need to add some terms in Suji transformation to cancel that one, to protect delta satisfy Suji algebra. This is coordinator method. So this is a brute force one, but maybe this is the most strong method. Not systematic, but this is And for some case, we can use supergravity to find the curved space Suji. Because supergravity contains, of course, gravity. So we need to decouple the gravity. But to have a solution, we need to, for example, we need to have the solution with the metric described as S3. But usually S3 cannot be the solution of the S3. But if we add some VB to the auxiliary field in a supergravity multiplicator, then sometimes we can find such manifold as a solution of the theory, and which keeps the supersymmetry. Then using user supersymmetry transformation or supersymmetric action with with that VB to the auxiliary field and taking G Newton goes to zero limit, we have a rigid, use a supersymmetric quantum field theory on curved space like S3. We can sometimes use such things. It's given by the Feduccia-Seiberg first. Then it's systematic and it's okay. But sometimes it doesn't work, like for the hypermultiplet case. That case we need a pure spinor like treatment. It's just done by Peston first for the S4 case. So in that case, probably we need to do some brute force things like that. Okay. Anyway. Then first things we can see is okay, so to show the supersymmetry algebra, we need to take the commutator of this delta. Then there's some derivative of epsilon appears. But on a flat space, epsilon is a constant. It's a constant spinor. So it's okay. But on a curved space, this band doesn't vanishes. Okay. And if this is a generic one, then we cannot expect any finite order cancellation of the such terms. Okay, so we need to something, and here or usually we may need the Killing equation or some generalization of the Killing equation. In this case, in this S3 case, this Killing equation, like things works, is defined by of course epsilon and epsilon m is the same because it's the same representation. Okay, so this is a Killing equation. It's a covariant derivative of the epsilon. A covariant derivative of spinor is proportional to gamma m epsilon itself. Okay, and this should be this factor should be this one because of the curvature is related to m, and the commutator of the dm gives a curvature. So to satisfy this equation, coefficient is fixed by this one. If this type of epsilon exists in a theory, and actually, if this Killing equation exists, we can construct the bilinear of this Killing spinor. Sorry, this is called Killing spinor. Then bilinear of the Killing spinor gives a Killing vector. Okay, so the manifold should be some isometries inside that, if this exists. Okay, but of course, in S3 case there is such isometry, so it's okay. But actually, we will not explicitly write down. We can solve this Killing equation S3, and there is a solution. Two types of solution, and we can use such a Killing spinor. And this there is some choice, but we will use a plus sign. This is just a convention. It's physically it's same. So Okay. Then this dm epsilon is related to gamma m epsilon. Okay, so there's no derivative like that one. So then, if we add something here, then we can expect the Suji algebras remain on a curved space by expanding by m. Okay, and then you doing such a calculation, it's yeah, it's not so easy, but if you do that, but not so bad. Only the change is this one. If we add this term to the delta d, this is order m, then we will see this supersymmetry transformation satisfies the supersymmetry algebra. Okay, extra term or extra term cancelled. So yeah, just this works. And for delta f, or for chiral superfield, we need to add 3 over pi to alpha minus 1. Oh, sorry, upside, bow, psi. Okay. Now here, R is called R charge. R charge. Maybe this is confusing. Anyway, charge of phi. Okay. And this R charge is mu sigma lambda bar d phi bar psi bar f bar. It's like R charge we have seen before. 1 minus 1 0 R minus R minus 1 R plus 1 R minus 2 R 2 minus R. So this is not good. 1 minus R. Okay, this is a charge. Okay, we assign this R charge. And yeah, but here the interpretation of R is we can forget about the interpretation of R or something like that. With this R, the Suji transformation is consistent with the Suji algebra. We can add these terms also. That is a claim. Okay, and R, if R is 1 over 2, this is called a conformally coupled chiral superfield. So this is a, conformal case. Conformally coupled chiral means if the theory is superconformal on a flat space, then we can conformally map the R3 to the S3. Then the Suji transformation or action also can be mapped from the R3 to S3 case. Okay, that case is corresponding to the Suji algebra with R equal 1 over 2. Okay, this means conformally coupled chiral superfield. But okay. Actually, this is a choice. If you want to consider the conformal case, we need to fix that one with the correct one. Yeah, if you know the R charges of the given CFT, it's yeah. So we can consider any theory on any theory on S3 with a different one, then it's a different theory, just a different theory. Yeah. Uh-huh. 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 Yeah, this R charge means if the theory is super conformal, then super conformal field theory includes the R symmetry. Okay. Then this R charge is a R symmetry, charge of the R symmetry. It's in a super conformal algebra. Okay, but if we consider not a conformal field theory, we can consider anything on S3. Then this R is just some given something. And so this is a choice, like a mass or something like that. It's a choice. Yeah, on R3 there is such choice, but on S3, actually there is a many term, can add many terms, and this is also, yeah. With this choice, with this R, if it's non-zero, non-zero, it's 1/2 or different, then, yeah, action also depend on the, supersymmetric action also depend on this R or something like that. So it's like that. No, just stop here. So that is good things. Yeah, this procedure is there is no guarantee it's stopped at a finite order. But in this case, or in a known case, always it stopped at somewhere. And in this case, this is just here. And actually there is no correction to the other field. Actually, in user notation, here we shift D by D plus sigma or something like that with D plus M sigma or something like that. But yeah, it's okay. This is okay. Okay. Then we can consider Suji action on 3. Okay. This is also given by like this method, order by order, or using supergravity or any other method, or conformally mapped. Using a conformal map from the R3 to S3 or something like that. Yeah, but this method can be applied to any case if it works. Okay. Then the only change is, in this case, this one. And of course, this dm includes curvature correction. Okay, this dm is a covariant derivative on S3. So it includes a Christoffel or the this one spin connection. Actually, it is not so easy to check this is invariant and this transformation. So you may check that one, but here I don't do that. Almost every formula cannot be checked explicitly with for a short time, so I just give some result. These parts are same as for the n equal 1 on flat space, as you see. This is a kinetic term, and okay, this is a coupling between the this includes a mu here. So if we take the a0 is a sigma, so there is this term sigma squared 5/5 or something like that here, and this is a user. This also comes from this one gamma 0 a0 or something like that, gives this term. Okay, and this is a curvature correction. Okay, and this also stops at this order, and this gives psi bar to the mass. So this psi is massive because of the curvature. Okay. Actually, so on S3, there is no zero mode because of this curvature. Okay.
From looking at the Lagrangian node, how do you so you've got some kind of new parameter you've expanded. How do you know that's associated with S3 without
Parameter means this M or M.
So I understand that you've got some curvature to express the mass term, and you've expanded that mass term. But how do I know that that's curvature from the Lagrangian?
Curvature from the Lagrangian, this M. Actually, M is not a curvature. It's like the magnitude of curvature, something like that. Yeah.
My question is, how could I look at this and see that S3 translates this M parameter?
Sorry, on S3. Actually, yeah, here we should use some property of the killing spin on S3 and everything on S3. We can use some, for example, in S3, the commutator of the dm proportional to the Ricci scalar or something like that because of the special rotation or something like that. Here, to check this one, we use everything. S3 have a SU2 cross SU2 symmetry, or we can, we should use this one here. Okay, so then if this manifold is not S3, it's not so symmetric, then this cannot be like this simple. It's very complicated. If it. This one? Yeah, of course, yes. Sorry, that is that's okay. Sorry. Okay. Okay, so this is action. Okay, and then in a 3D there is a this is a user of kinetic terms. This is no matter one in 4D, but in 3D there are other types of the coupling. Invariant action. It's a Chern-Simons action. In 3D, there is a Chern-Simons action. It's a gauge invariant for at least SUN. U1 case is a bit not simple, but anyway, like M, N, L minus lambda lambda 2 sigma d minus 4 m squared sigma squared. So you can check this is invariant under the Suji transformation and also invariant under the gauge transformation. Yeah, this is the user of Chern-Simons terms, ADA plus a cubic. Okay, this is invariant because of something related topology. Okay, K is called level of the Chern-Simons theory, and it should be quantized. I mean, it should be integer. Okay, and there is in a supersymmetric completion there is a lambda and sigma d. So this means lambda is this is just a mass term. Actually, Chern-Simons term doesn't have a bulk degree of freedom. It's a topological. There's only the boundary degree of freedom. So the corresponding super partner, lambda, should not have a bulk degree of freedom. And actually there is no kinetic term, and this is just a mass term, so there is no bulk degree of freedom, so it's consistent. And on S3, we need to add this term. This term cancels everything coming close. Of course, D, acting on D or this term, everything cancelled, including this term. Okay, you can check that. So this is called Chern-Simon term. And also, we can add the Fi term. Fi term is important in 3D compared with 4D. 4D case, it's introducing Fi term gives non-asymmetric free. So it's phenomenologically very important to break the supersymmetry, but it's not good for the theoretical consideration. But in 3D, Fi term is good. So this one, this is called Fi term. It's Fi term is this is a parameter, and D is so Fi term is linear in D. Linear in D. That is Fi term. Okay. And if we add this term, then it's supersymmetric. You can see that from the this case. It's easy to see. This is indeed invariant. Okay. And the superpotential. This is the invariant. If its R charge of superpotential is true, and without any correction. Actually, superpotential does not have a derivative, so there's no, I mean, covariant derivative or something like that. So it should be invariant without any correction. Okay. Of course, this is of course needed even on a flat space. Okay. So I do not write down, but this is same in a flat space, and it's supersymmetric. And also we can add a mass term by it's mass term by introducing if the theory have a flavor symmetry, a UNF or something, then we can gauge that flavor symmetry and weakly. And if we take the such a weakly gauged theory goes to zero limit, then the gauge coupling is zero, and it becomes a flavor symmetry again. And that procedure is done for the computing, for example, the anomaly calculation or something like that. And in that case, we can introduce a background gauge field like F or something like that, or background Wilson loop or something like that. And then we can introduce some, and corresponding background superfield. We can give this VB to the sigma. Actually, vector multiplet have this scalar component. If this give out this one, then it acts like a mass in a theory for the flavor. It's called flavor gauging. Like here, you can say this is a sigma squared. Okay, if you introduce some additional gauging of something, there is another sigma here, sigma squared. It gives a mass, the 5/5, and also here this 5/5. This sigma have a VB, then this gives a mass. Okay, so it's called flavor gauging. But okay, and this is manifestly Suji invariant if we add VB only to this sigma, not other one. Okay, so this is the correspond. Yeah. Okay. Anyway, of course this is constant. M is constant. So by these types, very generic supersymmetric action for general supersymmetric field theory on S3. So here we do not specify any matter content. We can add any gauge theory with any gauge group with any gauge matter. Any matter, which is any representation of the gauge group. Okay. Then observable. This observable means something supersymmetric operator, which can be computed in a localization technique. The supersymmetric called its supersymmetric Wilson loop. It's like this. Okay, and this part is of course use a Wilson loop. R is a representation of the gauge group, and this this trace or this A is represented by the representation matrix of R. Okay, so there's a choice of the representation for this Wilson loop, and this is a additional term which is needed to keep the supersymmetry. Okay, sigma dl. Dl is so dl is a line element of this circle C. C is a loop winds along Killing vector. Killing vector means epsilon bar gamma m epsilon. Actually, this S3 case, S3 is like a S2 and there's fiber S1. It's called there's a non-trivial S1 fiber. We can construct S3 like that. It's called a hop fibrillation. And this is a hop called a hop fiber, this S1. And this Killing vector is like that fixing S2 and rotate around this S1. So this is a Killing vector direction. Okay, so C can be this one. So it is a great circle of the S3, and there's no I mean, okay, so actually there is no fixed point, no fixed point for this Killing vector here. You know, for S2 or S4 case, Killing vector should have a fixed point. Like for S2, if you rotate some direction, there should be a fixed point, like a north pole and south pole. Okay, then there is some additional term in a localization technique, and it's a bit not simple like so S2 and S4 case, there is some fixed point of the Killing vector, and it's yeah, we need to consider some instant-on corrections on the singularity of the Killing vector. But this case, S3 case, there is a nice one. I mean, there's a nice Killing vector which doesn't have any singularity here. Okay, and this Wilson loop is anyone in this such a generated by such a Killing vector. Okay, you can check that this one is also supersymmetric. I mean, this is supersymmetric invariant for some choice of the delta. Okay, then the localization. Okay. Fiber deep side bar df bar. It's like that. Times expectation exponential LG plus LM plus dot. And this we tree level. So we want to consider the partition function of the original theory. This dot means maybe we can add this Fi terms as superpotential, Chern-Simons term, etc. So we call this one. And maybe we can insert W alpha here or something like that because it's also supersymmetric. And localization is okay. Localization is adding this here plus t delta b, and t goes to infinity. Okay. Okay, so we will take a 5 minutes break, and okay. Next, we compute one loop something and have a formula. So from 10, okay.
I'm missing a single line.
はあ、一番最初の講義の方で一節。ははははあ、同じ話。デカップルするってのは同じ。あ、別に、この辺の話だと、とにかくカイネティクタームが、の無限大のタームを入れれば、その下でデカップするっていう。まあ、ちょっと微妙な面はあるんだけど、まあ、基本的には、それ自体同じ話。というか、全部、ワンループのところもそうだし、カイネティクターム無限大があったら、デカップルして、フリーになる。OK。Okay, let's start. Okay. Okay. Okay, so we will start. It's now we consider the supersymmetric localization of this theory. Okay, acting everything. Okay, and delta v is a delta lambda. Lambda is okay. We can do like that, but here instead there's a simpler. Simpler way to localize the theory. It's like epsilon bar epsilon bar sigma 5 plus m minus 1 5 bar 5. Actually, we can show here is bosonic. Okay. Then if we compute transformation of delta, delta epsilon bar means Suzy transformation with delta equal, sorry, epsilon equals 0, epsilon bar non-zero only. And here, epsilon bar equals 0. Then if we compute this one, delta epsilon bar, then delta epsilon, then it's proportional to kinetic term for the Lagrangian. Of course, it's a supersymmetric invariant. And of course, we can take this as 1. Here, this computation is in a notation epsilon bar is a bosonic spinor. Then it's 1. And this one is also gives Lm. This is also a kinetic term for the chiral multiplet. Okay? Okay, so we can forget about this one. Okay. So we can take this part as V. This part means this part V. So this LG itself is a delta V. Okay. So this can be a plus or minus t times LG plus Lm. Okay. Actually, this gives a bit different one for the chiral multiplet, but this also works. This also works, but yeah, we can do that. This is a standard on S3 in a literature. Okay, so that means the path integral is localized on the zero mode of the kinetic term. It's very simple. And remember the kinetic term? You remember? T goes to infinity limit. Then Lg equals kinetic term for the vector multiplied is there is f squared, so f is 0. And dm sigma squared, so it's 0. And of course f squared is 0. D squared equals 0. And Lm equals 0 means this is a bit not so trivial, but this at least for 0 R2. Here we can see this one. Okay. The localization point is very simple. Just a point on a color superfield. So color superfield is all color superfield becomes massive, and for the gauge multiplied, gauge field is flat, so we can take A equals 0 and B equals 0, and only the things is dm sigma equals 0. So there is a constant, covariantly constant. Then and this is a scalar, so this means just a constant of scalar up here. Okay, so the partial integration becomes an integration over this 0 mode of the sigma only. Okay, it's just an integration. Okay. So only the constant. A is a constant. This is a saddle. And then, as we have seen in a midterm model, this becomes a T times free part. Plus and for example, this part is like del phi squared, and this part is T times gauge coupling to phi or phi bar. Anyway, plus, okay, so this is a function of phi. Then we rescale this phi, or the field in everything, for the massive mode, except this mode. Okay, it's like T phi equal phi hat, or something like that. Okay, then this becomes a free part plus interaction plus L3 phi hat over root T. And here, but this is like that. Okay. Okay. Then by rescaling, and here we goes to take T goes to 0 limit, so T goes to infinity limit. So then this interaction terms dropped out, like midterm model, and this also becomes 0. Okay, then in the T goes to infinity limit, it's just a free part, free field theory like del phi squared plus L3 part. But here, only the saddle. Saddle means all saddle means this condition. Okay, so only the here sigma, saddle means sigma equal A and other equals 0, and A is constant. Okay. Then we first integrating out this free part. This is free, so we can do that. Just a free field theory. Then remaining one is just an integration over this A for the saddle point. So then we want to compute the path integral. Of free part. And then here, after gauge fixing, this is like a Lorentz gauge. And then we can think sigma and A hat gives like a Higgs effect. Okay, and sigma is eaten by the gauge field, by the Higgs mechanism. And then, of course, we can do more precisely, but gauge fixing goes cancelled by this sigma integration. Okay, so it's like a massive gauge field plus fermion, and we can forget about sigma. Okay, it's included in some scalar mode of the gauge field. Okay, so this kills some one component, and of course, gauge invariance kills another component. But here, there is sigma, and sigma is like a third, the other component of the massive mode of the gauge field. Okay, then LG for this massive mode, non-zero mode is like on S3 vector plus adjoint A hat minus it becomes like that. Here, lambda adjoint is A adjoint means adjoint action of A to the lambda. Okay, this is just a rewriting of the free part of the LG. But we forget about the sigma because of this gauge fixing. So A hat satisfy this gauge fixing. So it's like transverse gauge field. Okay. Okay, this is a Laplacian for the A hat, and this is something like a D star D star D. Sorry, D star. This is like this. It's a kinetic part of the D. Okay, it's clear. Okay, so A is coming from sigma in the interaction, and so then we need a harmonic expansion, or Fourier expansion, or harmonic expansion on S3. And of course, symmetry is SO4 acting on S3 is SU2 times SU2. Okay, so of course it is no. This is some basic things in mathematics. So J 2 over J. This number is J plus 1 squared. Okay, so the value of the Laplacian is so it's like that. Okay. Okay, for scalar case, as you know, for the S2 case, you know it very much. Its harmonic expansion is characterized as a spherical harmonic function. It have a spin 0, 1, 2, 3, 4, 5, 6, etc., etc. And S3 case, it's given by the spin J over 2 for this SU2 and spin J over 2 for this SU2. So if J equals 0, it's a scalar, and J equals 1, and half is a vector in S3. Okay, and this is given known, and spinor case. Spinor case is because of the spinor indices, there's some shift. Like that. And sorry, this is a multiplicity. Multiplicity, this is a spin J over 2. So multiplicity is J plus 1. And there is, of course, there is a J plus 1 multiplicity, so it's a J plus 1 squared. And this is multiplicity J plus 1 times J plus 2. Well, this is just SU, representation of SU2. So spin J over 2 representation of SU2. And this one is like and the divergence-less vector. This case also the shift of spin 2. And the multiplicity is J plus 1 times J plus 3 from this. And eigenvalue of the Laplacian is J plus 2 squared. So this is a known result. We can see that in the formula. Okay, then vector H. So one loop determinant of the vector multiplet is pi j 0 determinant adjoint minus ia minus j minus 2 determinant adjoint minus ia plus j plus 1 j plus 1 j plus 2 over determinant a squared plus j plus 2 squared j plus 1 j plus 3. Okay, Is okay? Okay, this is yeah, just expanding this one by this Fourier expansion or harmonic expansion, and we have some eigenvalue. It's the eigenvalue plus UM squared A or something like plus 2m IA or something like that. And this factor come from the fermion. It's in a upside. I mean, so how do you get this expression? Yes, yeah, actually, yeah. For the fermion, it gives just integration of this free fermion gives a factor over this one. Okay, so then this is this one. This is sorry, it's a Laplacian or Dirac operator eigenvalue. Then this part is this one. If we expand it like that, plus there is plus m plus this one or a adjoint or something like that. Then okay. So and m is, we can say m, a dependence of m is cancelled, so we can take m equal 1 over 2. Then this is 1 plus 2 something like this one. And there's a plus minus, so another one is this one, j minus 2, j plus 1. This comes from this one. It's a boson. It's a boson, so the Gaussian integral gives this denominator. And this is just this one. Okay? And this factor, j plus 1 something, is a multiplicity of this one. Actually, there is a, this is like this is a angular, total angular momentum is like j, so there is the other label. It's have a same eigenvalue set. So this multiplicity is here. There's yeah. This is just a free theory. It's just a decoupled something. Okay. And this determinant adjoint means this is the adjoint field. So we also have some summation over the root system over that. So this gives a determinant. Okay, of A or something like that. Then, okay. So for example, for the fermion, there's a factor is like j plus 2 times ia plus j plus 1 or something like that. Okay, so j run for some dot. So then there's something j plus. If we fix a j, there's something like this. Okay, minus j plus 1. Okay, so if we pair these things, then this gives some minus a squared minus plus a squared minus j plus 2 squared plus. Okay, this gives a squared plus j plus squared, this combination. Okay, then this factor cancel this one. Okay, there's a j is j0. So this j can be 0, 1, 2, 3, 4. This gives 0, 1, 2, 3, 4. So this combination gives this factor a squared plus j plus 2 squared. It cancelled this one. Okay, so almost many things are cancelled each other. I mean, fermion and boson. But in this case, there is something remains. For example, this one, there's, for example, some j equal 1 case. There's here. So it's ia plus, yeah. So there is there's some remaining one. Okay. And remaining one in the in this formula is like Okay. So there is some j. So this factor is like a j plus 1 squared plus 2, something like that. And yeah, so there is some cancellation, but remaining ones we can see is this one. You can check that by carefully considering the j index. J, because j equal should be greater than 0, so something remains. Okay, and we can rewrite this one by alpha delta plus a alpha to sine hyperbolic pi a alpha squared. Okay, we can use some data function like regularization. This gives this one. Okay, this is a result for the one loop determinant for any gauge group. But maybe for example, this means that delta plus is a positive root, and it's over the positive root. And yeah, for example, A is like A1, sorry, here we expand A is HA. This is a Cartan. The matrix like this one. And then, for example, for UN case, A is like A3 dot to AN. So the N Cartan, it's a diagonal part. Okay, so this factor is like this is just sorry. So the root for the U1 case is like or 0, 1 somewhere. So this is just a A1, A2, or then A alpha is something like A1 or A2 or something like that. Is okay? So this part is also not real, but you can use some formula. Okay. And then another thing is d alpha. dA here. This includes, of course, the Cartan part. We fix the Cartan part at some value. But to fix that, there is some Van-der-Monte determinant by fixing to the some fixed Cartan part, like this HA. And the Van-der-Monte determinant is well known. It's in a matrix model context, like this one. Okay, this is called Van-der-Monte determinant. This is come from this is like we want to integrate over the matrix, n by n matrix. Then if there is a symmetry of the UN or something like that, then we can integrate over this Cartan part, but to fixing the gauge, fixing the actually this is a Jacobian for the measure for the matrix like 1 to this one by unitary transformation or gauge transformation or group transformation. Okay. So that means okay, including this factor, this times this one. So this part is cancelled. Okay. So for the one loop factor for the vector multiplicator is just this factor, sine hyperbolic squared. Okay. And the integration is over the Cartan subalgebra, DAI. And for the chiral multiplet, we can do same way. So it only includes boson, scalar and fermion. And from the kinetic term, we can see it's like this. This is user. Okay. This is for the scalar and this is for the fermion psi. And also we can use the phi and phi bar and psi bar, and we like this. Then it becomes, after some cancellation, it's like that. Okay. Here for the vector multiplet, this alpha is for the root, for the weight of the adjoint representation. Here for the matter, it's a chiral multiplet is some representation of the gauge group, and omega labels the weight of the gauge group. Weight of the representation of the gauge group for the chiral multiplet. For example, if you consider the fundamental representation, omega runs 1 to n or something like that. Okay. And here S b equal 1 is okay. Here S b, this one is called the double sign function. Okay. This is defined by this infinite product, and this have some field periodicity for the two direction. So it's called double sign function. Oh, this is sorry, x. And here we take a b equal 1 here. Then this gives us this one. Actually, if scarce or some quotient ellipsoid, not S3, then we can have a double sign function with b equal not 1. But here we consider the round sphere, not symmetric one. Then we have this one. Okay. So this is the result. And at saddle point, Chan-Simon and Fy term and others, superpotential terms 0 and kinetic terms 0. And then on the Wilson loop, is also evaluated at the saddle point. So just the insertion of expand 2 pi a. This comes from the supersymmetric completion, B sigma or something like that. Oh, sorry. Oh, okay, so finally, the partition function or correlation function becomes using these one. We assemble these results together. Then, like if there is a Chern-Simon term plus like Fi term if exists times trace R exponential 2 pi a. If we insert Wilson line, so and if there is a vector multiplet, I mean the gauge theory, then there's a factor like pi a alpha squared. And times, if there is a matter, we add this one. So this is the final result for the computation on S3. Okay, this is just a integration over. This is a number of the this integration is rank of the gauge group. Okay, so this is our integration. And if we integrate out, for example, for SU2 or some simple case, we can explicitly integrating out this one and some compact form of the action. Okay. So finally, we consider the large. Yeah, using this one, consider the large limit of AVGM theory. So AVGM is a 3D n equal 2. Sorry, in AVGM theory is a theory in 3D, and in 3D n equal 2 notation, it is something gauge group is UN cross UN. So there is a vector multiplet for this UN cross UN. And plus for bifundamental. Bifundamental chiral multiplet. Okay, so bifundamental means n times n and n bar representation. N for this first UN, n bar for this UN. This is called bifundamental. So component is n squared. So it's look like it's similar to the adjoint. Okay. Okay, and the Lagrangian is I times 4 pi k times Chern-Simon action, or supersymmetric, supersymmetric Chern-Simon minus I 4 pi k Chern-Simon prime. I mean, so this Chern-Simon action is for this first UN, and this first Chern-Simon is this second. Okay, and the level of the Chern-Simon is different. I mean, the sign of the level k and minus k. This is very special. And plus superpotential. So this part is very complicated. Superpotential proportional to phi quotic. So if we choose the superpotential very carefully, actually very carefully, n equals 6, this theory becomes n equals supersymmetric, superconformal field theory. Okay, this is expectation. And why this theory is interesting? Actually, this n equals 6 supersymmetric 3D theory is very interesting and very special. Its existence of this one is highly non-trivial. And the theory on the M2 brane, and in a low energy limit, at low energy limit, it becomes, it is described by the ABJM. It is claimed on the using a supergravity side. This becomes M on ADS4 times S7 over ZK. Sorry, maybe the M on some GK action. If you don't want to this one, just consider K equal 1 case, then it's this factor is nothing. So this is ADS4 times S7. So this theory and this theory should be ADS CFT type dual. Okay, these two should be same. Okay, and then using a localization technique, partition function of the okay, sorry. For this theory, with boundary is Z3, we can compute the partition function using just 3 gravity, supergravity computation. And the result is like this one, 3 over 2, 3 over pi square root of 2k times n over 2 over 3. If you using this is the CFT, actually n over 2 over 3 is like 1 over Newton. Okay. So this comes from the 3-level action. This is corresponds to 1 over Newton constant. Okay, so this is from the computation in this side. So this factor is a bit strange, not n squared or n. Fractional power of n appears here. Okay, so this is very strange from the field theory side, but after the localization technique, we can compute this partition function in a strong coupling side in ABGM. That means n goes to infinity limit with k fixed. Okay, that is just of course a weak gauge gravity limit. Okay, sorry. Okay. Then okay, the partition function can be computed using localization, and the result is what we have obtained. And there is a Chern-Simon term. This is a 3-level action because superpotential vanishes at a fixed point by the localization saddle. So only the Chern-Simon terms appear here. And if we rewrite A as lambda here, and for the one loop factor, so this is from the one loop vector multiplet. This is from UN cross UN. This is sine hyperbolic squared. Okay, this log is this like a free energy, not something. And plus for the bifundamental. So this summation is over the adjoint representation. Now adjoint is I minus j or something like ij or something like that. So this is for the bifundamental. And this double sign function for the vector-like chiral multiplet, it reduced to the cosine hyperbolic. So it's much more tractable. And because this is a bifundamental, lambda I minus lambda j child appears. Okay, this is for the first UN, this is for the second UN. Okay. Then we can compute so this integral. Then we have a exact results of the partition function for the ABGM theory. We can do that for the n equal to 2, 3, 4, or lower n explicitly. But here, we want to consider the large n limit. Then in the large n limit, of course, we can use some saddle point approximation, okay, stationary point approximation, and saddle point means 0 equal d lambda I df, 0 equal d lambda tilde df at large n. In the reading of the large n, if this is 0, so then this integration is stationary and it gives a dominant contribution. Okay, so this is a user approximation. It's like a if it's like a minus f something, it's like a 1 over h. So h bar goes to 0 limit, then the stationary point of this one does appear. It's a classical type, type. And okay, so naively, f will be n squared because there is a ij summation. So this gives a n squared, and this is log something. So this cannot be a factor of n to something. So it looks like this free energy will be n squared. It's natural because this is un cross un. The degree of freedom is n squared, not something. Okay, this is n squared, but we will see. So because it's in a large n limit, we can consider this label I as a continuous parameter, like S. Okay, so I over n is like a continuous parameter in a large n limit. So then we make some ansatz. Lambda S equal root n. Okay, so this is just a division of lambda to the g1, g2. But this special combination, and here we think g1 and g2 are order 1, not depend on n. Okay, then after some computation, it's actually non-trivial, but we can compute this F, free energy. This one for this ansatz. Then there is some cancellation between the n squared between this one and this one. I mean, vector multiplet and chiral multiplet contribution cancel each other for n squared, and we have 4 pi root k to the 3 times ds ig1 g2 plus dot over 1 plus g2 squared. we have a very simple expression for this one with this continuous notation. Okay, and power is this one because of the some cancellation between these two. Okay, and then saddle point equation is 0 equal dz1 df and 0 equal dz2 f. So this is dz2 plus 2 del s del z1 dot squared times 1 over 6 plus z2 squared. And then this one IG1 plus 4G1 dot G2. And also on the boundary, because this equation, actually there is a boundary. It's from I to n, so S have a boundary, okay? And there is a dot, I mean dot derivative. So this saddle point equation have some boundary condition by the partial integration, and this is a boundary condition. Then using there is only one solution for this equation, and the solution is z1 equals square root to s, and z2 equal minus 2 over I s. This is simple, and so this is a large n saddle point solution. So this should be represented by this one at the leading order in large n. Okay. So yeah, of course, this is a plus order, and we neglect such a non-leading term in large n expansion. We neglect such things. Such things are corresponding to the loop effect in a quantum gravity side. Then inserting this one into this one again, then this is the final result. The partition function, I mean log of the partition function. Okay, using this one. And this precisely match, I mean including this coefficient, match with the gravity side computation. Okay. So these types of the computation in a large n limit is usually impossible for the non-supersymmetric theory. But here, we can compute such things because of the localization technique gives exact result, including any strong coupling effect. Okay, so and it indeed matched with the supergravity computation. It's very nice. And actually, and there are many applications of this type. If you consider S1 cross S3, it's like almost S3. Then we can check the Seiberg duality using this localization technique. We can check some quantity on the Seiberg duals, and we can check that it matches, or AGT, it's related to S4 partition function and the Liouville theory on S2 or something like that. But there are many different and various things we can do in a localization technique, because the localization technique can apply any supersymmetric field theory. Okay, so if there is a supersymmetric field theory, you can apply this localization and have a exact result. So maybe you can use these techniques for your own problem, and so it's nice. And this, yeah, it's all the time. So yeah, thank you very much.